In the next section, I want to briefly show you what is used in Python these days. We'll cover the part where I had an influence on, and I'll show you some bits of the full algorithm, but there will be a few more things we don't cover. There's some lovely videos online that cover the rest if you're interested. So first of all, just to get the name straight, when people say Python, they often mean the program that you run, or they mean the reference implementation, but these are technically different things. So Python is just a specification. It's one long document or a website that tells you something about an eponymous programming language and how that is supposed to work, but it's not something you can run. It's not a program. Instead, the correct term would be CPython, which is the reference implementation of the Python programming language. And it's called CPython because it's written in C. But that's all. If you install Python, that's usually the implementation you get. But there are others available. It's not the only one in existence. And so Python, again, defines two ways to sort things. You probably know this. You can either have a list and say .sort. Then it modifies the list in place. It modifies the list to be sorted. Or you can call this sorted built-in function and pass a list, and then you get a copy back that is in sorted order. Now, despite this being Python code where you say sort, the actual sorting algorithm is written in C. And it's bloody low-level code that I'm happy I didn't have to touch. So this was, the low-level code was done by Tim Peters, who invented Timsort. That's the algorithm that Python uses for well over 20 years now, which is similar to the type of merge sort variants we've seen. It tries to exploit runs in the input that are already in order. Well, I gave this away already. Well, it was included in 2021. The official release was last year. So instead of Timsort, it uses the merge policy I'm showing you soon. Here's a rough overview of what Timsort looked like. And I just want to give you that to the extent that you can understand why people want to do this instead of the merge sort variants we've seen so far. The way roughly it works is as follows. And you don't need more of these details. So that's, again, kind of a side story. I think the whole section is outside of the exam, except for the high-level ideas. So Timsort goes one time through the entire array. There's no recursion in that sense. And it maintains a to-do list of things still to be merged. It's a little bit like this bottom-up merge sort. It's closer to that. And so in this case, we maintain this as a stack. It's not a queue like in bottom-up merge sort. The organization is a bit different. So you make your way through your list. You sit at some point, and you find the next run by code similar to what I had on the slides earlier. And you store that on your stack. That's on your to-do list. You eventually have to merge that run into the rest of the runs. Now, when and exactly how you do this is governed by a set of rules. I don't really want to explain in detail because I think they're just not a great solution and have never been, but that's the first thing that kind of worked, Tim Peters' words. So there's some rules that tell you, okay, now among the topmost runs, you merge a few or you stop. And it can go on for a while, and eventually it stops. Then you find the next run, put that on the stack, and keep going. Eventually, you reach the end of the input, and then you might be left with some things on the to-do list, so you just go top down. We'll see an example with this with the new merge policy in a second. I want to point out why this is a reasonable way to go about sorting. One thing that's good, I mean, it can pick up existing runs. But the second bit, our peak sort would have done too. The second bit is it keeps the locality of reference. That's, again, something to do with the hardware and caches. But if you read this run, you already spent the time to get that data to memory. So it would be useful to do something with that data while you have it. And that code, because it uses a stack, it's likely to do merges with the data it just loaded to memory straight away, as opposed to like peak sort, look in the middle, oh, now I know where to cut, and let me now forget that I touched this run and do something else. That's not as efficient. That's why people like Timsort. That's one reason why it's fast in practice. There are many other little tricks. I'll link to a few YouTube videos where someone explains those in a high-level language. As for fun for you if you enjoy it, otherwise you can forget about it. I just want to mention that I'm not doing the name Timsort justice if I would claim that that's all. There's other things going on, but they haven't changed. The story started with a few researchers noticing that there's a weird thing happening in Timsort's merge rules. So these weird rules here, the way to read them is that these are the lengths of runs. And so this rule would say if the topmost run is longer than the third run, you should merge the second and the third. And yeah, it's not intuitive. If you do this, it occasionally happens if you have specific inputs that something stupid is done. Again and again, you have very long runs where you just add a single element into it. So the red is the result, but you have this run that is just one element shorter. And then you spend all the memory cost of loading this, merging it, and writing it back to just get the run one element longer. That sounds very wasteful, and indeed it is. So it's 50% costlier than necessary for long enough inputs. In this case, it's 370 against 320. It's not 50% yet, but if you increase the size, this is just a handful of elements. So something's broken there, and you can do it differently that works better. That's what Powersort tries. On the left is the code, which looks very similar to Timsort's code. It's going through the list once, it finds the next run, it maintains a stack of runs that it still has to merge, but the rule when and how runs on the stack are merged is different. I think it's actually much easier. Each of the runs has a so-called power, and you just maintain that the powers are increasing on the stack. And if the new thing that you put on top is not increasing, then you have to merge. So I'll show you how this works. What I don't show you on this slide is where these powers come from. There's a function here that says compute a magic number for this run. Now, I'm not going to tell you what it does on this slide, but on the next one. So the way it works is you find the first run, and you throw it on your stack. And there's a 0 at the beginning. That's kind of a dummy value at the start. You find the next run, and you always have 2 runs in your hands. You compute the power of the boundary between them. Powers are really just at the boundaries, not the runs. Then you throw this on the stack. As long as this is increasing in power, it's fine, and you keep it. Now, if you go on, the next thing you put on top is not increasing. 2 is smaller than 3. And that means something's wrong, so you have to merge. And you merge the topmost things. So these are out of order. The 2 is too big. The 3 is too big. 3 has to go. So you merge those 2. And the result of a run always inherits the smaller of the power. And now everything is nicely in order again. If you go to the next step, you'll find another run. And again, 1 is not bigger than 2. So the 2 has to go. And we do that by another merge. OK. From then on, if you find the next boundary, it has a power of 2. If you stick that on the stack, that's fine. That's increasing. 2 is bigger than 1. And 1 more is also bigger. So nothing immediately happens. But now we reach the end of the input. And so from now on, we just take the topmost 2, merge them, and keep going until nothing's left. Juk, 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 and done. So what I hope you can take from that example is if you have these blue numbers that are magically given to you, it's very easy to decide what to do. You just have to check if the new thing that you put on top of the stack is bigger than what you have there or not. And you do this in the loop. So as long as the topmost thing is too small, you keep merging. Now, where these powers come from, I'll motivate with some animation. So pay close attention. Top-down merge sort is good because the merge tree is balanced. That's the essential part that makes it effective. So we'll try to mimic this. The problem is that we can't use a topmost cut like this if it's in the middle of a run. So we have to somehow round our merge tree to use these cuts that are there, but we'll take inspiration from that green tree. So the green tree is what we would do with top-down merge sort, but we don't want to do it exactly like that. So instead, we take the midpoints of the runs, middle of that run, and you imagine they are connected by a line. And then you let these lines fall down until they are stuck on some of those green poles. So you take the green tree to stop those blue lines from falling down. Let me just show it one more time so you get the visuals. But yeah. Where do the numbers now come from? They are just the depth of these nodes in the green tree. So that's the root. It has +1. It is at level 1. So that boundary gets power 1. And the next two, the children of the root, these have 2. So they're giving power 2 to these runs. And what this does is it imposes an overall balanced tree that a boundary that is essentially in the middle-ish will get power 1. And that's a good last merge. But it does this taking into account where the actual boundaries are. All right, so that's the power definition. And if you pull the tree straight so that it aligns with the boundaries, then it looks a bit more like the trees we had before. And that's the merges that you would do. So now you may wonder how this connects to the left to right version in Timsort. But you can show that the merges that Timsort does when walking through the array and doing this stack is exactly what happens here. So you're never explicitly building the tree, you're just internally using it as a virtual tree. There are many other ways to define numbers that have some properties like this, a global balance. The good thing about defining them in the way we did it here is that this is a local property. It doesn't depend on any of the other runs. It only depends on the two runs where we take the middle point off and where they are in the overall picture. It doesn't look at what the other runs are like. And if you want to know the details, this is how you compute powers. I'm not even sure I want to explain it in more detail. It's exploiting that you can approximate this green tree by cutting things in half repeatedly. And cutting things in half repeatedly is something you can do with dividing by powers of 2 and checking the binary representation of numbers. That part is not so hard to figure out, but it's quite annoying to explain. So I'll just leave it with the code and the intuition of these bars sinking down. To wrap up, first of all, Powersort is a replacement for one part in Timsort, namely the merge policy, that part that decides when and in what order to merge runs. All of the other things where the code for Timsort works well is not changed, so that's all kept. And that's the locality of reference. It's not having recursion, which is useful for space, and some other tricks like the galloping merges. But unlike Timsort's original policy, you have a provable upper bound on this merge cost that's close to h plus 2n. And like Timsort, it costs almost nothing to determine these powers, so it's cheap to do.